So let's now use our circuit model to implement basic arithmetic operations. And we start with addition. The circuit that is able to add two integer numbers given by their binary notation is called the adder circuit. So we'll talk about the adder and about its main efficiency parameters, size and depth. So let's pose the problem itself. The adder circuit is the circuit that is supplied with two numbers given by their binary representation. So let's suppose that we have numbers x with bits x0 through xn-1 and y given by its binary representation y0 through yn-1. And when we add these numbers, when we add them, we get a result z0, zn-1, and actually we can have carry bits here while we're adding these two bits, so the resulting number would have n+1 bits. And so let's now talk about this circuit, the adder, which takes as inputs these Boolean values x0 through xn-1 and y0 through yn-1, and produces many outputs from z0 through zn. So this would be our adder. Let's just implement it, mimicking what we are doing when we are adding these numbers by hand. So what we do is that we add the LSB, the least significant bits, and we compute the result z0, and possibly we have some carry bit c1 which goes into the next position. Then this c1 is added with x1 and y1, and the result is the next bit here, z1, and possibly the carry bit into the next position, and so on and so forth. So the zn, the last output, is actually the carry bit which was produced in the nth-1 position. So how do these z0, z1 up to zn depend on the inputs, on xi's and yi's? We see that z0 is actually the result of XOR of x0 and y0. If they are two zeros, then the resulting bit z0 will be 0. If they are 0, 1 or 1, 0, then z0 is 1. But if they are both 1s, then we'll have a carry, but the resulting bit here will be 0. So the carry bit c1, which goes into the next column, is equal to 1 only if x0 and y0 are both 1s. So it's actually the conjunction of these two guys, x0 and y0. Now, as soon as we look to the left in this scheme, we see that for all larger indices I, zi would be the result of XOR of xi, yi, and the carry bit which came into that position, and the carry bit into the next position, ci plus 1, would be equal to 1 only if out of these three bits there are at least two ones. And actually we have a special function for this kind of computation which is called the majority function. It's denoted by maj frequently, and this is majority function of xi, yi, and ci. So this function outputs 1 as soon as out of these three arguments we supply it with 2 or 3 ones. If there are just 0 or 1, one among these three arguments, then the function outputs 0. So this is a function which outputs just the value which is most frequent among the arguments. Okay, so we can now use this bunch of formulas just to create building blocks for our main circuit, for our adder. Now, it's super easy to compute this. One is just one operation. We already have a circuit for this thing, so for XORing of two variables. So we had this circuit before. We can take any of the circuits that we had here. So let's just take this circuit. And we see that actually in this circuit, we already have a node that computes the conjunction of the two inputs. And so really we can compute both carry bit C1 and the output bit C0 by the same circuit. So using 4 gates, we can compute both of these first bits in this scheme. So we can say that we have a building block, which we can denote by sigma 0, which is supplied with two things, x0 and y0, and it outputs two things as well. It outputs z0 and the carry bit c1. And now we can use these formulas to build a circuit which would look like this. So it has 3 inputs. It has inputs yi, xi, and ci, and it computes 2 outputs. It computes zi and ci plus 1. So this circuit can be called sigma I. Well, actually, this circuit is not different for different i's. So it's the same for I equal to 1, as for I equal to 2, as for any other larger than 0 index I, right? So because we just use a circuit which computes summation modulo 2, which is XOR, and the majority function for the 3 given inputs. And now, as soon as we have these building blocks, we can just combine them to create a circuit which adds multi-bit input numbers. And how can we build this circuit? So we'll not use this particular representation because it's just not convenient to draw when we have X inputs on the right and Y inputs on the left. It doesn't matter. We'll use a slightly different picture for this circuit. So we'll supply the inputs in on the picture in the order in which it is convenient for us. So we'll start with x0 and y0, and here we'll place this sigma 0 block. Then this block would give us z0 and c1, which we'll use together with the inputs x1 and y1 to get the next output z1 and yet another carry bit c2, which will supply to yet another copy of this circuit. Sigma 1, we can mark it again, and together with x2 and y2, this will produce the output z2 and the next carry bit, and so on and so forth. So up until we have zn as the last output. So this would be actually the carry bit cn. It's the same as we denote here by zn. So what are the efficiency measures, which are called actually complexity measures, because we have the complete complexity theory. So what are these efficiency or complexity measures for these circuits? What is its size? The number of gates. So the number of gates for these circuits, we know exactly the number of gates is equal to 4. And actually, we could prove that with some kind of brute force enumeration or some clever enumeration, that we cannot do it better than that. We cannot compute both conjunction and XOR of two variables with less than 4 gates, assuming that our base is conjunction, disjunction, and negation. We'll not do that. And we'll actually not try to get the most efficient implementation of this circuit. We can say that, okay, this circuit can be implemented somehow so that it has some constant number of elements in it. And then we see that this larger circuit, the adder circuit, has size which is proportional to the number of inputs, because the number of circuits of type sigma 1 that we'll use is essentially equal to the number of bits in the input numbers. So the size is big theta of n, or the size of input numbers, and the depth of the circuit is equal, well, unfortunately, it is also equal to something proportional to the number of inputs, because we have this longest path from, say, x0 through the carry bit c1 to sigma 1 through the carry bit c2 to sigma 1 that computes the z2 output, and so on and so forth. So we have this path which has length also proportional to the number n. So the depth of our circuit is theta of n as well. And currently we have these parameters of our circuit. While size parameter is pretty efficient, so it's somewhat intuitive that if you compute something non-trivial of n inputs, you cannot use like fewer than n elements, and this is actually easily seen whenever we have bounded arity of Boolean operations, because we need at least to combine several inputs into one output value. So whenever we have an output which in principle depends on all the inputs now, and we have only binary conjunction and disjunction, as soon as we apply a single element of conjunction and disjunction to two values, these two values turn into one value. And so if we need to turn n values into one, now how many times do we need to apply the operation? Well, proportional to n, actually at least n minus 1 times. Now, as for the depth can be made much, much better than linear. And actually the depth here for the adder can be made logarithmic. So this is what we'll try to do in a couple of moments. But before that, we'll once again reinforce this construction of canonical DNF of a function. So let's see that we can actually construct a circuit which computes both of these guys. So how do we do this? Let's try doing it at least in some detail. So we take xi, yi, and ci, and we can list all the possible values that we have for, say, our majority function of xi, yi, and ci. Here we can list all the possible combinations of the values of these variables, and we are listing them in canonical order, so by the order of growth of the corresponding integers for which these guys are binary representations. Or we can say that this is a lexicographical order of these tuples. So the next one will be 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Finally, actually there's a nice mnemonic rule for this table that we have half zeros, half ones in the leftmost column. In the next column, the period would be twice smaller, so we have 2 zeros, then 2 ones, 2 zeros, then 2 ones, and so on. In the next column, the period would be twice smaller as well, and so on and so forth. So in this way, the truth table can be easily algorithmically built for any given number of variables. And the majority function outputs 0 on all the tuples that have majority of zeros, like this one, and this one, and all the tuples that have majority of ones, it outputs 1. Our function looks like this. So now we can have this function constructed by disjunction of several elementary conjunctions. Like we take a conjunction which outputs 1 just on this tuple, and this conjunction is xi negated yi ci. Next we take conjunction that outputs 1 just on this tuple. This would be xi yi negated ci. Then the conjunction that outputs 1 just on this tuple, so that would be xi yi ci negated. And then finally the conjunction that outputs 1 for the tuple of all ones. This is the product of all of them. And so the disjunction of these four conjunction gets us the value of the function. For any input value tuples, so we have exactly one of these guys turn into 1 if the tuple is among these ones. And if the tuple is among the zeros of the function, then nobody out of these four will raise hand and say that, okay, so I'm responsible for this tuple, and thus in the large disjunction we'll have all zeros, and the disjunction of all zeros gives us 0. So then we can build a circuit based on this formula. And actually we can, just by looking at the formula, say what will be the number of gates in the circuit. So we have at most 2 elements, well actually we have 2 elements of conjunction at each of these terms, and we have at most 3 elements of negation. So whatever the function of 3 variables we have, we will use at most 2 elements of conjunction plus 3 elements of negation per elementary term like this. And then we'll have to employ at most 7 elements of disjunction, because we have 8 values maximal in total, so 8 terms in total here to glue together using disjunction. So this would be the maximal number of Boolean operations, the maximal number of gates thus in a circuit that implements a function of 3 variables. And so we have at most 12 elements in this function, and as well we'll have at most 12 elements in the circuit that computes the XOR of xi, yi, and ci. So we can actually immediately see that the size of this circuit, sigma 1, does not exceed 24. If we just take each of these 2 functions, this one and this one, separately implement it with a circuit, and just take the kind of union of these 2 circuits and denote this by sigma 1. So we know, by the way, that actually this theta for the size is not greater than 24 times n. Well, actually it's much smaller than that. So now as for the depth, when we want to go from linear depth to logarithmic, we'll need to implement some bright idea here. The idea which will get us rid out of this chain, out of this vicious chain from x0 to the zn, and this chain is here because of the carry bits. So we cannot compute the next carry bit before we compute the previous one. Well, at least this is our process of computation, which we remember from college. But we can try to compute these carry bits much faster. And this is called the carry look-ahead adder. And this adder would be a special case of a more general scheme, which is called parallel prefix computation, which we'll discuss in the next video.